Hello. Today we will be discussing soil compaction. So again, the reference book for this discussion is Principles of Geotechnical Engineering, 7th edition by Braha M. Das. So before anything else, let us enumerate some of the advantages or the benefits that the compaction gives us. It increases soil's unit weight, it decreases undesirable settlement, and it increases soil strength. So compaction in general is the densification of soil by removal of air, which requires mechanical energy. So the degree of compaction of a soil is measured in terms of its dry unit weight. So when water is added to the soil during compaction, it acts as a softening agent on the soil particles. The soil particles slip over each other and move into a densely packed position. The dry unit weight after compaction first increases as the moisture content increases. So it is highlighted here or really indicated here that the unit weight after compaction first increases as the moisture content increases, because later on the following discussion we will be talking about the behavior of the dry unit weight of our soil along with the moisture content increase. Alright, so we have here um, the compaction curve of a soil or a certain type of soil. So we have here in the y-axis for our unit weight or the unit weight axis, and we have here along the x-axis we have our moisture content, and we have here moisture content 1 and then moisture content 2. So basically in here our moisture content actually is increasing, and so is the axis for our unit weight. So note that at moisture content W, the moist unit weight gamma is equal to the dry unit weight or gamma D. So according now to this statement, at moisture content equals 0, no, this one, um, our unit weight is equal to our gamma dry or our gamma 1. So nasa da rin, no? It is stated here. So initially, our unit weight is equal to the gamma dry at moisture content equal to 0 or our gamma 1. So basically we'll be talking here the relationship or how um, our moisture content is related, or our moisture content behaves in a relation with its dry unit weight, and vice versa, no, how our dry unit weight behaves in relation with our moisture content. So munang first ko situation at moisture content is equal to 0. So mo na siya dani. So at moisture content is equal to 0, our initial unit weight is equal to gamma 1. So when the content is gradually increased, no, um, and the same compactive effort is used for the compaction, the unit weight of the soil solids in a unit volume gradually increases. So mo ni siya, no, along with the increase in our moisture content, um, we have also an increase in our unit weight, because we know, no, if we consider this y-axis, the values of our unit weight are actually increasing along with the increase of our moisture content. So for example, we have here at moisture content equal to W1, our unit weight now is gamma 2. So kaganiha, our moisture content equals to 0, atong unit weight is naara diri, no? So as our moisture content increases, niabot siya W1, now the unit weight of our soil actually increases as well. So it now becomes gamma 2. So however, the dry unit weight at this moisture content is given by, mo ni siya, no? Actually, it's the unit weight at moisture content is equal to 0 plus the change in the dry unit weight. Pero as we have observed also in the curve, no, although our unit weight increases as our moisture content increases, um, we can notice that after reaching moisture content 2, which is W2, which gives us the peak value or the highest value among this or along this curve, which corresponds to the highest dry unit weight of this soil. Any increase in the moisture content beyond this point, no, this peak point, or beyond this moisture content that gives us the peak point, our dry unit weight actually decreases beyond this point. So throughout this discussion, we will be discussing how this behavior is being affected by a lot of parameters. So mo na siya, no? Beyond a certain moisture content or W2, no? Any increase in the moisture content tends to reduce our dry unit weight. So this phenomenon occurs because the water takes up the spaces that would have been occupied by the solid particles. So the moisture content at which the maximum dry unit weight is attained is generally referred to as the optimum moisture content. So matutong ingon ganihan, no? For example, our moisture content continues to increase. So for example, from moisture content 1, our water being added to our soil increases and it reaches a moisture content equal to W sub 2, then that would give us our peak value for our dry unit weight. So this moisture content that gives us the highest value of our dry unit weight, which we call maximum dry density, that moisture content that can give us the maximum dry density is what we call the optimum moisture content. Meaning, um, this is the maximum moisture content that our soil um, can have or can contain, so that it does not or its unit weight does not further decreases. So any further increase beyond this optimum moisture content will result in the decrease of our dry unit weight. So that is why, no, the explanation nga nung from diri magka increase atong moisture content, magkaanam pud og increase ang atong dry unit weight. Pero if maabot gyud siya sa yang optimum moisture content, mailhan limang optimum moisture content, no, kay diha man ang mo reflect or diha na to ma-attain ang atong maximum dry density. If we try to further increase our moisture content beyond this peak value, our dry unit weight decreases. That because the spaces that will have been occupied by solid particles are now taken up by water. So meaning na saturate na atong soil. Okay, the laboratory test generally used to obtain the maximum dry unit weight of compaction and the optimum moisture content is called the Proctor compaction test. So these parameters, no, the optimum moisture content and the maximum dry density are basically the parameters that we use, no, or the standards or specifications that we use in the actual field um, to monitor a performance, ano, to monitor the performance of our soil that we are using. For example, in the construction of our roads, we have the soil for our aggregate sub-base course, and then um, we have to know the optimum moisture content of that soil so that we can attain our maximum dry density, or maximum dry density, no, in the most simple words, muni siya ang state nga pinaka-dense na gyud ang atong yuta, nga it can no longer be compacted or it can no longer settle even in the application of loads. So that's why kani siya, in order for us to attain the densest state of our soil, we have to make sure that our soil actually has the optimum moisture content. So that's why prior to the construction of our aggregate sub-base course, we have to do Proctor compaction test para makuha nato ang maximum dry unit weight and optimum moisture content. So basically, we will be conducting a test that will identify our optimum moisture content for our soil to be used on the field. So in the compaction test, we have the standard Proctor test and the modified Proctor test. So let us take first the standard Proctor test. Okay, in the Proctor test, the soil is compacted in a mold that has a volume of 944 cubic centimeters. The diameter of the mold is 4 inches. So during the laboratory test, the mold is attached to a base plate at the bottom and to an extension at the top. So the soil is mixed with varying amounts of water. So mag-trial and error ka, no? Okay, so that you will be able to graph your compaction curve with varying amounts of moisture content. That's why you have to conduct a compaction test in each of your identified or preferred moisture contents. Okay, so this soil then will be compacted in 3 equal layers by a hammer that delivers 25 blows to each layer. So the hammer has a mass of 2.5 kilograms or 6.5 pounds and has a drop of 12 inches. So we will be further exploring or studying really the process of this test during our succeeding discussion. So mo ni siya no ang specifications for our standard Proctor test. Okay, alright, so mo ni siya no ang illustration sa atong typical nga mold and then atong rammer. So basically ang mechanism ani no, the soil with mixed with varying amounts of water will be placed here. So i-divide siya katulo no. And then sa kada layer, first magputang kag yuta dire, and then you will be compacting the soil using the hammer, no? And then on another layer, you will still be compacting it for 25 blows, and another layer, you will be compacting it for another 25 blows. So you will be conducting this test or using this apparatus on depending on how many moisture content that you would desire to conduct the test for. So mano yung mga dimension, no? We have 4.5 inches ay yung outside diameter, mani pero yung inside diameter is actually 4 inches, and we have the extension which will later on be removed during weighing na of our mold filled with compacted soil. So muna siyang rammer no which will be drop para makompact ning soil nga isulod nimo ani nga mold. So the moist unit weight of a compaction rather, gamma, can be calculated as gamma is equal to the weight over the volume of our mold. So the volume of our mold is actually known because we already know the dimensions man of our mold, and the weight of the compacted soil in the mold will be determined after weighing the mold every after trial of the compaction test. So if you divide that, you will be able to get the gamma wet, which is equal to the total volume, I know the total weight divided by the total volume. So for each test, the moisture content of the compacted soil is determined in the laboratory. So with known moisture content, the dry unit weight can be calculated as gamma dry is equal to gamma wet over 1 plus moisture content over 100. So this formula, we have already discussed this in our preceding discussion. So the moisture content here actually corresponds to the moisture content of the soil sample that we can get out of the mold na katong gitimbang kaganihan no. So kada mold magkuha tag soil sample or kada mixing sa atong water para sa atong soil nga ato i-compact, we will be getting the actual moisture content of that soil. So mo ni siya diri natong gamiton. So the values of gamma dry from this equation can be plotted against the corresponding moisture contents to obtain the maximum dry unit weight and the optimum moisture content. So you will be computing the gamma dry and the actual moisture content corresponding to that specific unit weight, and then you will be plotting that on the curve nga similar sa atong gipakita kaganihan no, and then from there you will be able to identify the peak value of our unit weight, which is our maximum dry unit weight or the MDD, and then the moisture content that would give us that highest value of our maximum dry unit weight, which we call now our optimum moisture content. Okay, the procedure for the standard Proctor test is elaborated in ASTM test designation D698 and the ASHTO test designation as T99. So these provisions, no, and or specifications established by these organizations present the standard procedure for the conduct of our standard Proctor test. So for a given, we also have another formula now, which we will be using in our standard Proctor test. So for a given moisture content W and the degree of saturation S, the dry unit weight of compaction can be calculated as follows. So depending on the given, no, as much as we did in the properties of soil related to the unit weight, no, the weight and the volume relationship, we can calculate our dry unit weight also using with the specific gravity and the degree of saturation of our soil. So for a given moisture content, the theoretical maximum dry weight is obtained when no air is in the void spaces, that is, when the degree of saturation equals 100%. Hence, the maximum dry weight or dry unit weight at a given moisture content with zero air voids can be obtained by substituting S is equal to 1. So, muna siya no ang formula gamma ZAV, wherein this is the maximum dry unit weight when there is no air in the void spaces or when saturation is equal to 100. So, mo ni siya no, ang atong gamma or the dry unit weight at saturation is equal to 100, we will be using this formula. So, when the problem asks us for the dry unit weight at when the degree of saturation is equal to 100, then this formula is what we are going to use. So, man siya no, gamma ZAV is equal to the zero air void unit weight. To obtain the variation of gamma ZAV with moisture content, use the following procedure. So, first, determine the specific gravity of soil solids. And then, second, we should know the unit weight of water. Kablo naman tayo, no? And then, we should assume several values of our moisture content, such as 5, 10, 15, and so on. So, use the equation to calculate gamma ZAV for various values of our moisture content. So aside from the standard Proctor test, we also have what we call the modified Proctor test for our compaction test. So with the development of heavy rollers and their use in field compaction, the standard Proctor test was modified to better represent field conditions. This revised version sometimes is referred to as the modified Proctor test, or with ASTM designation D1557 or AASHTO test designation T180. So basically, no, the mechanism of this modified Proctor test is just the same with the standard Proctor test, no? Same lang gyapon, mag-compact lang gyapon sa mold o ang atong yuta with containing varying amounts of moisture content. It is just that the difference between them is the size of the mold and the rammer that is being used. So for conducting the modified Proctor test, the same mold is used with a volume 944 cubic centimeter as in the case of the standard Proctor test. However, the soil is compacted in 5 layers by a hammer that has a mass of 10 pounds. So the drop of hammer is 18 inches. The number of hammer blows for each layer is kept at 25 as in the case of the standard Proctor test. So, mani siya no ang kalainan. First, we have this set. Mas gamay siya, no? This is for our standard Proctor test. Mas gamay ang mold and then mas gamay po ang iyang corresponding hammer. And then we have here, no, kaning naa sa left, is what we use for our modified Proctor test. So, pareho lang sila itsura, lahi lang sila size. Okay, so we have here, no, a table with the summary of the standard and modified Proctor compaction test specifications for. We have here the description, the method A, method B, and method C. So, depende siya, no, kung what type of soil or the particle size distribution of our soil that we will be conducting our compaction test for. So, natin diri, no, depende sa situation or sa type of soil. Depende po na dayon ang atong gamiton nga procedure. May it be standard Proctor test, method A, method B, method C, whichever is applicable. Or it could also be modified Proctor test, for method A, method B, and method C. No, kandalain-lain siya diri no, number of layers, the same lang sa standard Proctor test. Pero sa modified Proctor test, we have 5 layers na dayon. And then, ang height of drop, mas taas, no? Which is equal to 18 inches for our modified Proctor test, compare sa atong standard Proctor test, which is only equal to 12 inches. So, napunta diri, no? For our method C, for both the standard Proctor test and modified Proctor test, we will be using 56 blows per layer during our compaction test. So whichever is applicable for our soil characteristics that we have, diya magdepende kung what method and what type of proctor test that we will be conducting. So we have here example number 1. The laboratory test results of a standard proctor test are given in the table. So we have here the volume of the mold, no, which is actually constant because the dimensions of our mold or dimensions of our mold that we will be using is just the same. And then the weight of moist soil in the mold, no, nagkadalalahi siya, meaning sa kada trial ni siya or kada mixing sa tubig sa atong soil. So we also have the corresponding moisture content in each of these weight, no. First, we are asked to determine the maximum dry unit weight of compaction and the optimum moisture content. And B, we have to calculate and plot D, which is plot the dry unit weight versus the moisture content for the degree of saturation S, which is equal to 80, 90, and 100. And we have a given value for a specific gravity, which is equal to 2.7. So we first have the A, no, nga question. We are asked for the optimum moisture content and the maximum dry unit weight. So we will be using this formula, no, from the previous discussion. We have the gamma wet or just the gamma, which is equal to the weight over volume, and our gamma dry is equal to our gamma wet over 1 plus moisture content. So we have here, no, as our given, mura man ni kaganiha, the volume of the mold and the the weight of our soil. And then we have the moisture content corresponding to each of these weight of soil. And then from the given volume and from the given weight, we can simply get our moist unit weight, which is equal to weight, this one, divided by the volume, which is equal to this one. So we can get the value for our moist unit weight. So gibalin lang siya, no, ang kaning column for our moisture content, gibalin lang siya, gidikit lang siya sa atong dry unit weight. So later on, it would be easier for us to plot the curve. So since we already have our gamma wet, which is this column, no, and then we already have the values for our moisture content and varying moisture content, we can now compute for our dry unit weight, which is equal to gamma wet, no, kani siya nga column, over 1 plus moisture content over 100. Okay, kani siya nga mga values in percentage pa man. So that's why you would have to divide it with 100. And then from that, you will be able to get now the values of your dry unit weight. So with this value, we can now plot our compaction curve, no, with the gamma dry or the dry unit weight as our y-axis and our moisture content as our x-axis. So mao ni siya, no, katong mga moisture content ganiha, mo ni sila na nato siya pag-plot isa-isahon. And then that is now our compaction curve. So for example, no, at 10% moisture content, we can get the corresponding dry unit weight that you have computed. And then for example, for the next moisture content, we have the 12. So you are going to project that, no, and then get the corresponding dry unit weight. So basically, we already know how to plot man siguro, no, in a plane, no, in a Cartesian plane like this, and the values for our coordinates or our, this time, the moisture content and the dry unit weight. The moisture content as our x and the dry unit weight as our y. So mo ni kabali siya, no, ang atong compaction curve from the data that were given to us in the problem. So from that, we can identify, no, the peak value of our dry unit weight, which is this one. So mao ni siya no. And then the corresponding moisture content for that peak value of our dry unit weight is what we refer to as our optimum moisture content. Meaning, our dry unit weight is equal to this one, maximum dry unit weight, and the optimum moisture content is this one. So, meaning, ang implication ani no, our moisture content should already be or should always be equal to our optimum moisture content for us to be assured that our soil is in its densest state. So, for second problem, the following table can be prepared using the following equation. So, um, muna siyang gamma zav, no? The formula or the equation for that is already given, and we have already been given the value of our specific gravity and our wet unit weight, ganihan, no, in the previous solution, and then the moisture content, and then the saturation, which is already given in the problem. S is equal to 80, 90, and 100. So, kada moisture content, no, naa siya corresponding nga value for its dry unit weight. So, actually, dry unit weight is siya nga mga value, no? For example, we have 132.7 pounds per cubic foot nga dry density if our saturation is equal to 80% and when our moisture content is equal to 8. So, kani siya nga mga values, i-plot gapon nimo dito, no? With our moisture content still the x-axis and our dry unit weight, which is equal to our y-axis this time. So, if you're going to plot that, muna siya, no, ng manggawas. Still, this is the graph or the curve representing the moisture content versus the dry unit weight. So, muna siya, no, S is equal to 80, and then S is equal to 90, and then S is equal to 100, which is equal to our gamma zav. So, we call our dry unit weight our gamma zav, no? Our gamma dry is equal to our gamma zav when the saturation is equal to 100% rapod. So when our saturation is just equal to 80, so atong tawag ani nga curve is just the dry unit weight, no? Kani siya nga mga values along diri. Dry unit weight lang na siya. Ahead na to siya tawag og gamma zav if our saturation is equal to 100. So now let us talk about the factors affecting our compaction. Okay. The preceding section, no, showed that moisture content has a strong influence on the degree of compaction achieved by a given soil. Besides moisture content, other important factors that affect compaction rather are soil type and compaction effort. So the importance of each of these two factors is described more in detail, no, in our succeeding discussion. So basically, although water or the moisture content has a very big influence or impact on the degree of compaction for our soil, there are also other types or other factors that can affect our compaction, which is the soil type, no, kung ano siya ng klase nga yuta, and our compaction effort, kung unsa nato ang compaction energy, unsa ka, unsa nato siya pag-compact, our means of compacting. So we'll be talking that here. So first, let us talk about the effect of our soil type in our compaction. So the soil type, no, that is the grain size distribution, shape of the soil grains, specific gravity of soil solids, and the amount of clay minerals present has a great influence on the maximum dry unit weight and the optimum moisture content. So, mo ni siya, no, for different types of our soil, kay magdepende man daw gyapon ang atong compaction sa atong type of soil. So, we know naman tayo mga type of soil like the sand and the clay, no, for example. So, mo ni sila, no, in the previous studies conducted or on the previous test conducted on these types of soil, mo ni siya ang mga common nga porma sa mga compaction curve. So, lahi-lahi gid siya og behavior, no. For our highly plastic clay, inana siya, and iyahang range sa iyahang dry unit weight with respect to its moisture content is lower than that of the sandy silt. And then for poorly graded sand, ubos gid iyahang dry unit weight. So lahi-lahi gyud siya porma, no, lahi-lahi siya behavior according to its compaction curve. So meaning lahi-lahi gyud og performance or lahi-lahi gyud og degree of compaction nga ma-attain sa nagkadalay-lahi pod na type of our soil. So note that the bell-shaped compaction curve shown in for sands, the dry unit phase, for example, this statement here is actually referring to this compaction curve for our poorly graded sand, no? So the dry unit weight has a general tendency to first decrease. So maubos to siya una along with the moisture content increase, and then to increase to a maximum value with further increase of moisture content. So maubos na siya una, and then ahead rin siya mutaas, and then after reaching its peak value, no, maubos gyud siya. So that is common. No, that phenomenon is actually common to all types of soil. After reaching its peak value, maubos gyud siya with further increase in the moisture content. So the initial decrease of the dry unit weight with increase of moisture content can be attributed to the capillary tension effect. So at lower moisture contents, the capillary tension in the pore water inhibits the tendency of the soil particles to move around and be compacted densely. So you also have here the different shapes, no, of our compaction curve encountered in our soils or different types of soil. So Lee and Sudkamp studied compaction curves for 35 soil samples. They observed that 4 types of compaction curves can be found. So the following table is a summary of the type of compaction curves encountered in various soils. So type of compaction curve, you have A, B, C, and D, no? And then kung siyang itsura, bell shape ba siya, odd shape, and double peak. Depende siya actually siyang liquid limit. So kani silang duha, no? They have studied the behavior of compaction curve for different types of soil so that they would be able to classify, no? For example, a soil has usually its liquid limit belongs to the range nga 30 to 70. So most of the time ang iyahang compaction curve is bell shape or pareha ang itsura, no? For example, our soil has a liquid limit of greater than 70, then iyahang compaction curve will somehow look like this. So man siya they have given us an idea on how different types of soil actually behaves during compaction. So now the second factor that affects our compaction is the compaction effort. So the compaction effort or the compaction energy rather per unit volume used for the standard Proctor test can be given as, so E is our compaction energy, no, which is equal to muna siyang formula, we have the number of blows per layer, which is usually 25 man, no? So muna siya diri 25. And then the number of layers for our standard Proctor test is equal to 3. So muna siyang 3 pa siya di ano. And the weight of the hammer, mga tagay ng 2.5, um 2.5 times 9.8, so gi-convert lang ni dira yung weight, no? And then the drop of the hammer, which is already known, and the volume of mold nga known gyapon siya, no? So our compaction effort can be computed, no, in this value in this manner, and then we will come up with the value of our compaction energy, which is equal to 600 kilonewton per meter per cubic meter. So that is for the SI units, and for English units mo pod ni siya, no, kung English units, in English pod na mga values atong panggamiton each of these parameters. So if the compaction effort per unit volume of soil is changed, the moisture unit weight curve also changes. So this fact can be demonstrated with this figure, no, which shows 4 compaction curves for a sandy clay. So mo ni siya. The standard Proctor mold and the hammer were used to obtain this compaction curve. So the number of layers of soil used for compaction was three, yes, for all cases. However, the number of hammer blows per each layer varied from 20 to 50. So which varied the energy per unit volume. So the preceding observations, we can see that as the compaction effort is increased, the maximum dry unit weight of compaction is also increased. So first, we have this first curve, no? Ang gigamit daw niya is 20 blows per layer. So, mas ubos siya og dry unit weight compared sa 25 blows ang gigamit. So, pero mas madako pag yun ang yang dry unit weight as the compaction energy increases, no? From 25 blows and then 30 blows to 50 blows dayon. Kaya dito sa tong formula, for our compaction energy, isa sa dependent value is ang number of blows man. So, if the number of blows actually increases, our compaction energy also increases. That's why, along with that, no, depending on the compaction energy, no, if our compaction energy actually increases, the value for our dry unit weight also increases. So, kung mas kusog ang energy, mas makompact yun ang soil. Mo na yung marag rationale behind, no? So, as the compaction effort is increased, the optimum moisture content is decreased to some extent. So, the preceding statements are true for all soils. Note that, however, the degree of compaction is not directly proportional to the compaction effort. So, although, no, mag-increase in some cases, mag-increase gyud or maka-cause og increase ang atong compaction energy sa atong dry unit weight, um dili siya pwede ma-consider nga directly proportional silang duha. So now let us talk about the structure of a compacted soil. So murag gakaunsa man gyud, gakaunsa gid ang soil, no, during our compaction and its arrangement of the particles. So, structure of compacted soil, no? Lambe studied the effect of compaction on the structure of clay soils. And the results of his study are illustrated in here, no? If a clay is compacted with a moisture content on the dry side of the optimum, as represented by point A, kani, it will possess a flocculent structure. So this type of structure results because at low moisture content, the diffuse double layers of ions surrounding the clay particles cannot be fully developed. Hence, the interparticle repulsion is reduced. This reduced repulsion results in a more random particle orientation and a lower dry unit weight. So, in different moisture content, no, these are the different structures of our soil according to Lambe. Okay, so when the moisture content of a compaction is increased, no, as the moisture content daw increases, as shown in point B, so natas point D karon, no, the diffused double layers around the particles expand, which increases the depulsion between the clay particles and gives a lower degree of flocculation and a higher dry unit weight. A continued increase in the moisture content, no, from B to C, kani siya B to C, expand the double layers more. So this expansion results in a continued increase of repulsion between the particles and thus a still greater degree of particle orientation and a more or less dispersed structure. However, the dry unit weight decreases because the added water dilutes the concentration of soil solids per unit volume. So, mo na siya maubos daw siya dara, no? So, the given moisture content, no, higher compactive effort yields a more parallel orientation to the clay particles, which gives us a more dispersed structure. So, the particles are closer and the soil has a higher unit weight of compaction. So, this phenomenon can be seen by comparing point A with point E. So, better results gid or better orientation of our clay particles when we exert high compactive effort for our soil. And also, not just that, no, it will also give us a higher density or higher, yes, higher compacted density or higher unit weight for our soil. And now let us talk about the effect of compaction on cohesive soil properties. Okay, compaction induces variations in the structure of cohesive soils. Results of these structural variations include changes in hydraulic conductivity, compressibility, and strength, although these properties of our soil will be later on discussed, no, in the succeeding chapters or succeeding modules. So, results are shown, no, in the permeability test on Jamaica sandy clay. So, this graph here is actually a test result of the permeability test conducted on a Jamaica sandy soil. So, this graph is due to Lambe 1958, no, with permission from ASCE. So the samples used for this test were compacted at various moisture contents by the same compactive effort. So the hydraulic conductivity, which is a measure of how easily water flows through the soil, decreases with the increase of moisture content. So it reaches a minimum value at approximately the moisture content. Beyond the optimum moisture content, the hydraulic conductivity increases slightly. So the value of the hydraulic conductivity on the dry side of the optimum moisture content is due to the random orientation of clay particles that results in larger pore spaces. So as we can see here, no, with respect to our moisture content, our hydraulic conductivity or how our coefficient of permeability or our hydraulic conductivity. So first, let us define what is hydraulic conductivity. It is a measure of how easily water flows through the soil. So kung unsa daw kadali makasulod or makapenetrate or makaflow ang atong tubig through our soil strata. So murag it has also something to do with its permeability, no? The ability of the soil to allow water to flow through it. So meaning as our moisture content increases, no, diri ang ato ko nung hydraulic conductivity also increases. So, as magkadako atong moisture content, mas magkagamay daw ang chance or mas magkalisod makasulod ang atong water or maka-flow atong water through our soil strata. Kay mas magka-dense man siya, no, in our preceding discussion. As our moisture content increases, magka-dense man siya ang atong soil. So that's why kung magka-dense atong soil, um, dili na gid makaagi ang tubig, meaning it's already impermeable. Kay dense naman kay siya na no voids anymore nga pwede ma-take up sa atong water when it tries to flow through our soil. So if we reach, no, our optimum moisture content na diri, which has given us the maximum dry unit weight, no, after reaching that point of our moisture content, kibali mo ni siya, no, beyond that, or any increase in the moisture content of our soil actually increases our hydraulic conductivity. Although, dili man kayo inanakadako gid ang increase, pero increase gid siya slightly. So as the moisture content increases, because as explained kaganihan, no, it is due to the water taking up the spaces that should be actually taken up by our soil solids, kay increase naman yung moisture content. So muna siya, no, ang relation sa atong compaction or ang effect sa atong compaction when it comes to the hydraulic conductivity of our soil. So we can notice, no, on the dry side of the optimum moisture content, which is this one, our hydraulic conductivity actually is decreasing as well. So we also have the effect of our compaction, no, on compressibility. So one-dimensional compressibility characteristics of clay soils compacted on the dry side of the optimum moisture content, um, optimum and compacted on the wet side of the soil. So under lower pressure, a soil that is compacted on the wet side of the optimum moisture content is more compressible than a soil that is compacted on the dry side of the optimum moisture content. So this is shown, no, on A. Low pressure. Our A is actually the low pressure. The pressure tends to orient the particles normal to its direction of application. And under high pressure, the trend is exactly the opposite, no? Muna siya. So the space between the clay particles is also reduced at the same time. So, however, for samples compacted on the wet side of the optimum moisture content, pressure merely reduces the space between the clay particles. At very high pressure, it is possible to have identical structures of soil samples compacted on the dry and wet sides of our optimum moisture content. So, ang pasabot lang niya ani, no, on the dry side of the optimum moisture content or katong lesser niya, no, on the dry side, mas gamay on moisture content nga mas gamay sa atong optimum moisture content, and the soil daw is less compressible than the soil nga with containing moisture content higher than the optimum moisture content, or it's actually on the wet side of our optimum moisture content. So if you consider our optimum moisture content, no, the compressibility of our soil decreases, no, ano siya dali na? Actually, this illustration is related to the pressure. Actually, it is in the unified compression test of our soil, UCS. Kani siya nga data. Pero ang murag ang pasabot ani is um, if our moisture content is lesser, no, as our moisture content increases, our compressibility of the soil actually also decreases. And after reaching its optimum moisture content, no, any increase in the moisture content beyond our optimum will now increase the compressibility of our soil. So the strength of compacted clayey soils generally decreases with the molding moisture content. So this is shown in the figure on the left, no kani, which is the result of several unconfined compression or strength tests on compacted specimens of a silty clay soil. So the test specimens were prepared by kneading compaction. Figure also shows the relationship between dry unit weight and moisture content for the soil. So note that specimens A, B, and C have been compacted respectively on the dry side of the optimum moisture content, near the optimum moisture content, and on the wet side of the optimum moisture content. And the unconfined compression strength, QU, is greatly reduced for the specimen compacted on the wet side of the optimum moisture content. So some expansive clays and in the field, no, do not stay compacted, but they expand upon entry of water and shrink with the loss of moisture. So this shrinkage and swelling of soil can cause serious distress to the foundations of our structures. So the nature of variation of expansion and shrinkage of our expansive clay is also shown in here, no, on the left. So laboratory observations such as this will help soils engineers to adapt a moisture content for compaction to minimize swelling and shrinkage. So we can notice if our moisture content increases, our swelling due to wetting also increases, and no, the volumetric change actually decreases as well, and the shrinkage, no, due to drying, or the change in volume due to drying will increase as our moisture content increases. So muna siya, no, ang behavior sa atong shrinkage and swelling. So that's why it is very important to really be able to identify the optimum moisture content of our soil, so that undesirable effects of excess moisture content of our soil will be eliminated or avoided. So it is very important, good, for us to be able first, no, to identify our optimum moisture content and the maximum dry density or the maximum dry unit weight of our soil. So that would be all for now. The first part of the discussion for our compaction, no, the theoretical part of our soil compaction. So on the next discussion, we will be talking about compaction on the field, or the actual conduct and implementation and adaptation of soil compaction on the field. So that would be all. Thank you so much.